You ever just stare at a train map and think, where can I really go from right here, right now? Well, we're going to answer that question today. But here's the thing. What we're actually going to uncover is a super powerful way to solve, well, pretty much any kind of puzzle. So let's get this journey started.
All right, so here's the challenge. And it sounds pretty simple, right? We're starting in Vijayawada, a huge train hub in India. And the question is just this. What are all the places we can get to by train before the day is over, before that clock strikes midnight?
Okay, every good challenge needs some rules. So here they are. We're starting our journey on a Monday, right after midnight. That gives us a full 24 hours. We can hop on as many trains as we want, but, and this is the big one, our final arrival has to be before midnight on that same Monday.
Now, to do this right, we need a system. We can't just pick trains at random. So let's start with the very first train we can take on Monday. That's train 22203, leaving at 0055, basically 55 minutes past midnight. A few hours go by, and boom, we arrive in Secunderabad at 6:15 a.m. First city? Check.
Okay, so we're in a new city, and right away, we've got a choice to make. Do we go all the way back to our starting point, Vijayawada, and try the next train from there? Or do we see what's possible from where we are right now, in Secunderabad? You know what, to keep this organized, let's stick with this path. We're going to go as deep as we possibly can before we even think about turning back. Let's see how far this rabbit hole goes.
So we pull up the train schedule for Secunderabad. We're looking for anything leaving after we got here at 6:15. And it turns out there's only one option on a Monday. Just one. Train 22204 leaving at 8:15 a.m. All right, so where's it headed?
And here we go. Our first problem. This train actually has two big problems for us. First, it's heading right back to Vijayawada. We've already been there, so that's not helping. And second, look at the arrival time. It gets in on Tuesday. That totally breaks our one-day rule. So yeah, this path is a no-go. Invalid.
So what does that mean? It means this path is done. It's exhausted. From Secunderabad, there are 0 valid moves we can make. We've hit a dead end. This whole branch of our search, it's officially over.
So what happens when you hit a dead end? You backtrack. You gotta go back. We rewind to our last big decision point, which in this case was way back at the start, in Vijayawada. We have now explored everything possible from that very first train. So it's time to try the next train on our list.
Okay, but wait. How do we keep from going in circles or exploring the same place over and over? Our system needs a memory. Let's call it a travel log. It's simple. We mark a station as exploring when we're checking it out. And once we've looked at every single path from that station, we change its status to finished. That way, we know not to waste our time on a city like Secunderabad ever again.
All right, fresh start. We're back in Vijayawada. Next train up is 02245, leaving at 4:25 in the morning. Now this one's interesting. It makes a couple of stops that fit our one-day rule. First, it hits Renegunta, and then it keeps going all the way to Bangalore.
So, sticking to our strategy, we hop off at that first stop, Renegunta, to check it out. And what do you know? The only connecting train from there goes right back to Vijayawada. This is exactly why our travel log is so crucial. We look at our log, we see Vijayawada is still exploring, and we immediately know not to take that train. That's a loop. So, Renegunta, another dead end.
Okay, let's just take a step back here. Notice what we're doing? We're not just randomly picking trains. There's a very clear pattern. Go deep, as far as you can down one path, hit a dead end, backtrack, and then try the next path over. This whole systematic, exhaustive process, it actually has a name.
It's called Depth First Search, or just DFS for short. This is a classic algorithm from computer science, and it's designed for exactly this kind of thing, exploring networks. The name really tells you everything you need to know. We go for depth first. We explore one single branch all the way to the very end before we even think about checking out any other branches.
I mean, this train journey is the perfect real-world example of DFS in action. We could have checked all the immediate destinations from Vijayawada first. That's another method called breadth-first search. But we didn't. We picked one train and followed it to the end of the line. It's a really simple but incredibly powerful idea. Depth over breadth.
But that leads to an even deeper question, right? How does a process like this remember to come back to an earlier step? How does it finish up in Bangalore and then know, okay, time to go back to Vijayawada and try the next train? What's the engine under the hood that lets it pause one job, go do something else, and then pick up exactly where it left off?
Well, there's this great analogy for it.
Imagine a contractor working on a big project. And right in the middle, they realize they need to handle a smaller, but basically identical, side job first. So what do? They pause the big job, they take care of the small one, and when that's done, they come right back to the main project. The only difference here is the contractor is giving the job to itself.
And that little story? That's the perfect picture of the engine driving our search. It's a concept called recursion. This is a huge idea in programming. It's where a procedure solves a big problem by calling itself to solve smaller, bite-sized versions of the exact same problem, over and over until it hits a dead end.
So let's put it in terms of our journey. We start a main mission. Let's call it Explore Vijayawada. When that mission finds the first train to Secunderabad, it literally pauses itself, and it launches a brand new submission, Explore Secunderabad. That little submission does its thing until it hits that dead end and finishes. And only when it's totally done does our original Explore Vijayawada mission wake back up, right where it was, ready to try the next train.
And that's the absolute magic of recursion. It's the perfect tool for a depth-first search. Every time it calls itself, we go one level deeper into the problem. And when one of those calls finishes, we just automatically pop right back up to the level above, ready to check out the next option. It's beautiful, really. Okay, so now we know the powerful method we've been using all along, a recursive depth-first search. So let's circle all the way back to our original question. After this process has checked every single train, every single connection, and backtracked from every dead end, what was the answer?
And here it is. After our recursive DFS did all the hard work, methodically checking every valid path and backtracking perfectly, it spit out a final list of every unique city we could reach. We already found Secunderabad, Ranagunta, and Bangalore, but by exploring all the other branches, the system also found Balharsha and Nagpur.
Which means the final count is 5. Not a guess, not a maybe, but a hard, provable answer. 5 different cities. And we found them by using a logical, exhaustive process that would give us the same answer every single time.
When you think about it, what we've really done is build a giant tree of possibilities. We started at the root, that's Vijayawada, and we grew branches out to every possible next stop. We ended up with a complete map of every single place you can get to if you follow our rules.
And that kind of leaves us with one last big idea. We solved this puzzle for just one day, but what if you had 2 days or a whole week? The amazing thing about a method like depth-first search is that it scales up. Using the exact same logic, you could map out an entire country's rail network, one recursive call at a time. And really, it's not even about trains. It's a way of thinking that lets you untangle just about any complex web of choices you can imagine.